So today we're going to talk about sound propagation in the water environment. To make things more interesting, we are going to talk about sound propagation in a time-varying and shallow water environment. And I will explain why this environment is more important for us to do research, either do research or why we're interested in these environments. Okay, we'll start. Okay, I will design this question as the kind of interactive lecture, but it seems doesn't work very well in this online course situation. So I probably just give you an answer. So I always ask like, what do you think is sound? But I think you already know that already. Anything sound is a mechanical wave. Like basically it's a vibration, and what we hear is the sound in the air, which is the pressure fluctuation from its mean. So it's not static pressure, it's that deviation from the static pressure. That's the sound we can hear. And so the title of this lecture is called Sound Propagation in Time-Varying Shallow Water Environments. So I list 3 keywords here. One is sound propagation. Second one is shallow water. The third one is time varying. So why we choose this? So the second question can be why we study underwater sound propagation. The answer is that we study underwater sound propagation. We don't study underwater light or EM wave propagation. The reason for that is sound propagation is more effective than light or EM wave or any kind of waves in the water. Because if you think about light under the water, after 10 meter steps, there's no light at all. But for sound, the propagation can last for a very, very long distance, even cover half or like a circle of the Earth. So it's much longer, it's much more effective. That's why all the application in the sound is based on sonar, which is short for sound navigation and ranging. That means something. Yeah, sound navigation and ranging. So sound is important, quite important in the ocean. And then next question is why shallow water? Why don't we research deep water? Usually appear to people, they think deep water is much more complicated. But in fact, for sound propagation, shallow water is more complicated than deep water. You will see for shallow water, there are a lot of challenges. The challenges because the water depth is much shallower. And also, this shallower water depth is going to give us a lot of reflections. You send one sound signal, the sound keep reflecting back and forth between these layers. So that will give you a lot of trouble when you're processing the sound data. And the other challenge comes from the environmental variability. Usually the coastal area, the shallow water, the coastal area is going to is more dynamic than the deep ocean. We already kind of talk a little bit about that in the ocean dynamic course. In the ocean, everything is kind of slow, the wave height is small, but when you get to coast, like develop wave heights, the wave breaks, and all these things all happened in the shallow water region, like within the continental slope, like within the continental shelf. So it makes sound propagation more difficult here in the shallow water. And the other concern is compared to the deep ocean, shallow water area is more close to us. People are living near the beach. People are living near the coastal region. And a lot of ocean engineering activity are conducted within the either a river or like coastal area, in an estuary, or like not far away from the city. So they are more close to us, and we have a lot of effect for the ocean, and also ocean have a lot of impact for us. Think about the sound propagation. If you have an ocean engineering activity doing there, such as I don't know, such as piling, people try to build a few facility in the ocean. They have to like pile a hole and then put a pole there to steady the platform. And the piling process can cause a lot of noise, and the noise can disturb the marine life in the ocean. And they're conducting this in the coastal region. So they want to care about how these anthropogenic noise, that's what I call it, means noise made by human, how this noise propagates in the ocean, how they affect marine life. So there are a lot of concerns, a lot of interest in research ocean sound propagation is in the shallow water. And a few basics of the sound propagation here, you already know, I guess. The sound speed in the air is only 340 meters, but in the ocean, it's 1500 meters per second in the water. So it's going to be much faster than in the air. And that's an advantage to use sound in the water because it takes less time for sound to get there. And next question is, what physical property do you think of ocean water do you think can affect the sound speed in the ocean? So the answer is same as how physical ocean properties can affect ocean density. It's the same, it's just temperature, salinity, and pressure. And how? Then if I increase the pressure, do I increase the sound speed, or what's the relationship here? So a basic principle is that if the compressibility is higher, that means like compressibility. If let's say it this way, if the fluid is more compressible, let's compare air and water. Air and water, if the fluid is more compressible, in this case, air is more compressible than water. Which one will have higher sound speed? If you compare in this case, you can see, oh, the water will have higher sound speed because the water is less compressible. That means less compressible will give you higher sound speed. And they do experiment. They find water is less compressible at these few different conditions. Either you have high pressure, high temperature, and high salinity. So it's quite easy to remember. So in this case, if you increase the pressure, you increase the sound speed. If you increase the temperature, you increase sound speed. You increase salinity, you increase sound speed. So it's quite, the relationship is quite easy to remember. The conclusion is very easy to remember. If you increase these three parameters, you will increase the sound speed. And they have this is an empirical formula for calculating the sound speed from temperature, salinity, and this is a depth. But you can always in the water you can convert depth to pressure easily. You can replace that with every 10 meter is 1 atmosphere pressure. You can calculate with depth. So this is a function of these three. And we can take a look which one play a bigger role here. It's easy to see its temperature will play a much bigger role than the other two parameters. So if you increase temperature by 1 degree, you will increase 4.6 meter per second sound speed. But if you increase the salinity by 1 parts per thousand, you only increase like 1.4 meter per second sound speed. So it's much smaller. And the depth is even, the significance is even less. So major role that change the sound speed is the temperature. That's the dominant parameter, temperature. Okay, now we combine this with the actual ocean profiles. So this is depth. This is from 0 to 4,000 meter water depth, and they plot two parameters here. One is the temperature. Temperature is going to be this curve. This curve is the temperature. And they also plot the other curve is the salinity, which is like this one. And I want to point out the range here. The range for temperature is from 0 to 30 degrees Celsius. From like the surface to deep water is the range is 20 something degrees Celsius. But the salinity, the range is very, very small. It's only around 34 to 35. That's only like 1 parts per thousand difference. And this plot miss the pressure here, but you can see, as you can probably imagine, as you increase the depth, you will increase the pressure, and it's a straight line. It's going to be something like this. It's a straight line. They didn't plot it here, but you probably can already imagine that. And now they use the sound speed function that in practical formula we just showed in last slides. They can calculate the sound speed, and this is the sound speed looks like. So it looks like it slowed down at the surface, and then to a point it has a minimum sound speed, and then after that the sound speed keep increasing. And this is called the sound channel. This area is called the sound channel. That means the sound propagates very well within this area, or within this area, the sound can propagate for a very, very long distance. So it looks like it's a good channel for sound to go. So you can think this way. So they usually call this as a sound channel. And why there is a sound minimum form here? So that's a combination effect between the temperature and pressure. So this is how, if I change the temperature, how the sound speed change. So the curve is like this. Basically, it's like times 4.6. So remember here the change, if we do a partial differential, so this is partial t is going to give you 4.6. Partial c, partial s going to give you 1.4. And partial c, partial z will give you like this number. So you times that with the measurement you have, you will give this. So the effect of temperature will give you like this. The effect of the depth will give you like this. And if you add up these together, you will get some curvature like this, which is the sound speed, the true sound speed profile. Oh, by the way, they call this sound speed profile, or simply SSP. So if I see SSP in other slides, it means sound speed profile. So they will have this minimum sound speed at a depth about 1,000 meters, sometimes less. It depends mostly on the temperature profile. It depends on the season. It depends on the location. But usually the sound speed minimum is a range from 0 meter to 1,200 meters, probably within that range. And that one, that sound speed minimum depth is very important for the sound propagation. I think we will see that in a second. Okay. First of all, if the medium is homogeneous, the sound will travel like at a straight path, like a light. It will travel straight to you. That's in homogeneous medium. But think about if the medium is not uniform, it has two layers. If the medium has two layers, what will happen is the sound is going to bend. So that bending we call it sound refraction. And how it bends based on Snell's law. So basically the Snell's law is like this. You have two medium, C1 and C2, and you figure out the grazing angle. Some people use instant angle. So instant angle is this angle to the normal. This is the instant angle. But here I'm using the grazing angle. Grazing angle is to the horizontal. So this is a grazing angle. So the Snell's law give you that C1 over C2 is going to be cosine phi 1 over cosine phi 2. So one is for this medium, two is for the other medium. They have this relationship. This is the Snell's law. And if you know this relationship, and you probably can already guess which one, if you want to see this plot, if I ask which sound speed is faster or which sound speed is higher, you probably can guess if you apply this. But basically, the sound speed is slower here in C2, faster here in C1. We can take a look. At the beginning, it's important to understand it. So let's see. Right now, let's see the phi 1 and phi 2, which one is bigger. So for phi 1, so it's this. Phi 2 is this. So phi 2 is bigger. But remember, the cosine is bigger at small angle, but smaller at bigger angle, because cosine is like function is like this, right? So so phi 1 is smaller, will give us bigger C1, will give us bigger sound speed. So in this case, the sound speed bend like this. And we have a very, very easy to remember how the sound speed bend is that you can think sound as a very lazy person. He always bend to the slower sound speed. So for these two medium, the sound speed C2 is smaller, so it always try to bend to C2. So if I travel this way, I find this medium is slower. I'm trying to bend towards that medium. So that's the kind of easy way to remember sound propagation is sound is very lazy. First, second, why lazy? Because it behaves like it always try to pick the slower road. And next slides. Okay, and then we are going to apply that. Give me a second. Sorry about that. And now we're going to apply that. Sound is very lazy and it always bend to the slower medium. I give you three different, actually it's two different sound speed profile. So sound speed profile, as I mentioned, is the sound speed as a function of depth. That's what we call a sound speed profile. So for this sound speed profile, it means as the depth increase, the sound speed doesn't change. So this is kind of a uniform medium. And for uniform medium, we already know that the sound is going to travel in straight line. So it travel like this. This is the sound speed in uniform medium. Right now, if I change the sound speed profile like this is actually, we call it negative sound speed profile. Because as the depths increase, the sound speed decrease. So it's kind of have a negative relationship here. So in this profile, how the sound path will travel is it always bend to the slower sound speed. So the slow sound speed is deeper. So in this case, all the sound paths trying to go deeper. And it's harder to think at the beginning, you can think it step by step. So this is a continuous medium, but you can think that as they kind of have a smaller change in different layers. You think there's layer 1, layer 2, layer 3, a different layer, but the sound speed kind of keep getting smaller and smaller as you go deeper. And then for each layer, you can apply that Snell's law. Like the Snell's law is for 2 layers, right? For each layer, you can apply that Snell's law, and you can work out the relationship between phi and theta, phi and sound speed, and you will know, okay, it's keep bending this way. But if I reverse that, it will bending on the other direction. So eventually you will get curvature like this. But another way I like to think is just thinking about sound speed is very lazy, and sound is very lazy. You try to bend to the slower sound speed. Okay, the slow sound speed is deeper, so it bends deeper. That's it. I like to think that way. It's kind of easier and more straightforward. So if we think about this, there are a few different type of sound speed profiles, give us different bending of sounds. One example is negative. I already showed it bends towards the deep ocean. And there's an area, probably there's an area somewhere here. I will not receive any sound. Think about this. If the sound is bending towards the deep ocean, there is a point I reach the surface and I bend to a deep ocean. And above that, there's no sound. I can receive no sound. No sound is received. So that region, they usually call it shadow zone. It's kind of shadow is kind of borrow the idea from light. If the light cannot get there, it's dark, right? It's kind of create a shadow. So that's the shadow zone for sound propagation. And another type of sound speed profile is positive sound speed profile, which means as you go deeper, the sound speed is higher. And similar, sound is always bent to the slower sound speed. So the slower sound speed is at the surface. The sound is kind of bending this way towards the surface. And some people call this surface duct, because the channel right now it's focused on the very shallow regions, kind of forming a duct at the surface for sound to go. They call it surface duct. But anyway, so these two type of ray, and they call it down refracting, because all the rays refracting down, and this is up refracting. And if I have a sound speed profile like this, it has a maximum sound speed at a depth. What will happen is the sound path going to spread. Think about the above parts. Okay, the source. If I put a source here, and above the horizon, it will keep bending up. Below the horizon, it will keep bending down. Using that principle, because sound speed is smaller in both directions, so the sound kind of spread at this cases. Okay, so that's for sound refraction. And next thing we're going to consider is the boundary. Especially for shallow water, the boundary is very important, because you're not going to avoid that. You always have a surface. You always have a seafloor. So that's how sound propagation is different from the air, because in the air probably there's no upper limits or like different cases, but for shallow water there's always a water surface, there's always a seafloor, and shallow water, this seafloor is the steps is quite limited, so you can't avoid that. You have to have sound bouncing back and forth between these two layers. So, and that called multi-path, because if you send a sound, you don't get one received signal. You get a direct. Okay, let me use this fig to explain. So this is source. If I set a sound here, boom, and what happened is I receive here. This is a receiver. You may think, okay, the sound is going to travel straight to the receiver. That's the direct path. Yes, the sound will travel this way, directly to the receiver. That's one path. We call it direct path. And because there are two boundaries, there will be reflection between these two boundaries. So one example is reflected from the surface. So it travel to the surface and then go to the receiver. This is a surface reflection. Similarly, we can have bottom reflection, like this one. It travels to the bottom and then goes to the receiver. And we can have more than that. We can have bottom first, and then surface, and then receiver. We can either have on the other way, like surface, bottom, surface, receiver. We can have as many as we want. We can have a lot of paths. And this is give us a trouble, because if you think of this way, if I send a sound and there's only one direct path, that means I only receive one signal. If I send very quick peak, very short peak, ping, what I receive is ping, like this is the only direct path. But if I have multiple paths, for instance, this one, let's look at the surface reflection here. Compared to the surface reflection and this direct path, the surface reflection is, the sound is traveling, have a longer path. So this longer path will give us give sound longer time to travel. So it will receive later. So this one, if I send a signal here, and the first signal I receive is direct path because it travels shortest distance. And then I probably receive the other path. I think it's probably this one, like R10 here, because it's slightly longer than the direct path, and then we'll receive much higher reflections. Like we have like one bottom reflection, one surface reflection. This path is longer, so you will receive something after that. So if I send one ping, what I receive in the shallow water is a biggest ping at the beginning, and then have small ping, 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 a lot small signals after that. So that one is called the multi-pass effect, because you receive multi-pass signal. You don't receive one signal, you receive a lot of signals. And I asked question here, why the paths are opposite in, I think this is in, you can just see this figure. Sometimes the received signal, they have kind of opposite phase. For instance, the 1 is here, the 2 is, the phase is opposite. 3 and change again, 4 reverse again. Why they are, sometimes they are opposite? It depends on which medium you are reflected. So if it's reflected from the air-water surface, the phase is going to reverse because it's a pressure release boundary, or they call it shaft boundary. If you work out the Z1, Z2, the acoustic impedance here between these two, from a denser to lighter medium will give you like the negative acoustic impedance difference. So that one will give you the phase shift. So it depends on the medium. So for easy to remember is if the path is reflected from the surface, it will reverse the phase. So we can see this path 2 must reverse from the surface, path 4 must kind of reflect it from the surface at least once at all times. Okay, so that's kind of an idealized case. But in reality, the sound propagation, the multipath can be very, very complicated. Here has one example. So this is also a negative. This is a positive sound speed profile. The dashed line shows the sound speed profile. This is in Arctic. So if the sound is trying to travel this way because it's bending up, this is surface duct. The sound speed lower at the surface, trying to bend this way. But because there are in Arctic, these are sea ice. So these ice sometimes at some point, when you hit this point, the sound is going to travel in different directions because it causes scattering here. This is an example for that. And this is for like from open ocean to continental shelf. Oops. If the sound is traveling this way, okay, there are quite a lot of different paths. It can, for instance, this sound speed profile is very complicated. It has a surface duct, and then also have a sound speed minimum. So the sound speed minimum will focus sound in this area, but the surface duct will focus sound at the surface. So they kind of have many different paths. And then eventually when you travel to the continental shelf, the sound is all converged. So the sound propagation in reality is become much, much more complicated. That's why we need to study that. Okay, I think I'll cover 2 more slides and we will stop for this class. Another basic of the sound propagation is the transmission loss. Transmission loss is defined this way. It's because we know this when you talk about transmission, you know sound is keep going, right? And think about the spreading of the sound. At the center, the energy, let's say 1, and it travel 1 meter away. All these sound energy at this surface, 1 meter surface, if you add them together, the energy should also be 1 because it comes from this center 1, right? So, but right now this 1 energy is spread in like this surface. This surface is 4 pi r squared. In this case, if I get larger range, if I travel farther away, the surface is much larger. So the relationship A is 4 pi r squared. That means the sound energy, if you measure the intensity or the pressure here, it's going to reverse proportional to the range because the spreading is based on the spherical spreading. Yes, spherical spreading. So it's proportional to r squared. But in shallow water, because there is a limit between the surface and the seafloor, the spreading sometimes is not, you cannot consider as spherical. We consider a simple case as cylindrical. Cylindrical is that sound speed travel, but it spread in a cylindrical way. And you can work out the same thing. The A here for the cylindrical spreading is going to be what? Going to be this 2 pi r, the circumference of the circle times the water depth, 2 pi r times h. So it's going to proportional to r only, 2 pi r h. So the h is the water depth, it's not the not the radius. So it only proportional to r. So this is the difference for sound propagation in shallow water. Okay, I guess I will stop it here for today because we run out of time, and we will continue in the next class. Okay, the class is over. If you have question, you can stay and ask question. If not, the class is over. And I will see you guys on Friday.